Okay, are you just going to talk about regular lecture and then talk about what's going to be on the exam?
So the lecture time, I'll just give a regular lecture, but in the morning, what I'm going to do is I'm going to record a review video. Yeah, and so that'll be separate. So I'll post that on a Canvas, and so you can watch that as you're studying. Yeah, yeah. Normally, I like to record those the week before, but Friday I'm going out of town, so I won't be able to get a chance to. So I'll do it Monday morning. Thanks, you too. Get some water.
Ken?
Yep.
The last class is just a lecture, right?
Yes. Yeah, today is just a lecture as well.
You need to go back.
Okay. Yeah, we went over the midterm project last lecture. So.
Yeah, that's a part of the recording, right?
Yes. Yes. Mhm. Yeah, it should be the beginning of the recording.
Dr. Chan, can you hear me?
Yep, I can hear you.
Is it okay if I ask a quick question?
Sure.
So I had a chance to quickly review the midterm.
Yep.
I haven't actually read the details or anything, or look at the CAD files. I just checked out the PDF. And one thing I noticed is that the units are mentioned. So are there certain units, or you want us to use English units or SI
No,
units?
it doesn't matter to me. Just
Okay.
whatever. Just be consistent. That's the only. Yeah.
Sounds good.
All right, it's it's 7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Another riveting audience here in person. Yeah, no, I get it. It's late. It's tough to make it out here. Okay, so today is another lecture day, so it's kind of an off week, and so remember our ANSYS activities are every other week. So next week we'll be resuming with activity 4, but this week we're just lecturing. Right? So we're going to continue on with our theme from Monday, and so if you recall from Monday we talked about 2D element types, and so today we're going to continue that with 3D element types. Okay, I think we'll get through it pretty quickly, so I'm going to probably start on the next set of lecture notes, which is shell and beam elements. Okay, and so we'll talk a little bit about that. Why you would use shell and beam elements, because that deletes directly into activity 4. Okay? So the theme for the next couple of weeks is going to be meshing it. So we're going to talk about a lot about element types, different types of elements. What are some of the kind of more interesting things you can do with the mesh? Okay, because the mesh I think is the I think it's in terms of depth, I think it's definitely the deepest part of using finite elements, and it's the part where you can really kind of modify things a lot in your favor. Okay? So it definitely pays to talk about meshing quite a bit. Right. So I think that's all my announcements. Remember, the midterm project is out there, and so as of Monday, there was you had a month to do it, and so now it's a month minus 2 days, and so definitely make sure you take a look at it soon. Give it a try, load the CAD files, try running some simulations, because I guarantee you the simulation part, the activities make it seem like the simulation part is something that's quick to do. I think you'll learn very quickly that when you're working with a more complex geometry, it takes a lot longer to get the simulation to work. And so definitely give yourself enough time to give that a try and to kind of work through some issues and debug. Okay, because it'll take a fair bit of time. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. Let's talk about 3D element types. Okay, so last time we met, like I mentioned, we talked about 2D elements, and we introduced this idea of the shape function. Okay, and so just to kind of refresh your memory, every element, every combination of element shape and element order has a shape function that defines a lot of its capabilities, a lot of its characteristics. Okay. It's tough to kind of overstate just how important the shape function is. And so if you've taken 541, you're probably familiar with the shape function and how important it is. But really a lot of the behavior of a shape function, a lot of its characteristics, its cost, its solution behavior, how well it models geometry, a lot of it is based on that shape function. So you'll hear people in finite element talk about shape functions quite a bit because it is something really important. Okay. And so what we saw on Tuesday was the fact that, on Monday, what we saw on Monday was that, depending on how many nodes there are in your element, whether you include mid nodes or not, it's going to drastically change, what the shape function looks like. Okay. So we did that on Monday, for every combination of 2D shape. So we did the quadrilateral and the triangle, and we did them for linear and quadratic elements. Okay. So today we're going to do the same thing for 3D elements. And so we're just going to go right down the list and kind of list out kind of what each of the 3D elements look like. Okay, so let's start with the absolutely simplest 3D element, which is the linear tetrahedral. Looks something like this, and so it's basically a four-sided pyramid. So the way you draw it is you draw kind of two triangles that are kind of next to each other. I'll give it some dimension, and then you draw a line in the back to connect the two back nodes. Okay, and so in total, we have 4 nodes on this element. 2, 3, 4. And so we're going to follow the same logic that we did on Monday. And so if we have 4 nodes in the shape, this means our shape function is going to have 4 terms. And so here is the shape function. And so the big difference here is that now we're in 3D, and so we have to include the z direction as well. Okay, so we're not just x and y, we have to include z. So we have t of x, y, z. Okay. Right, so just like before, we're going to start with the constant term. And so the constant term has no functional dependence. It's just literally just a constant. And so that's C0. We have all the straight up linear terms. We have C1x plus C2y plus C3z. One term for each of the nodes in the element. Right, so this is about as simple as you can get. And so, we have our constant term and we have our dependence in x, y, and z. And so, linear dependence is basically the simplest you can do. And so that's kind of where it is. Right. And so on Monday, we talked about this connection between the number of nodes and the number of terms, but we didn't really talk about, why that is. And so why is it that, for each node we have a term? Okay? So I wanted to spend a little bit of today talking about that. And we're going to use the linear tetrahedron as kind of an example, because that's the simplest that we can do. Okay. So why is it
Dr. Chan, I have a question.
Sure, what's up?
So we've been talking about triangles, tetrahedrals, squares, and hexahedrals.
Yep.
Do you think that in the future there might be a shape that is even more optimized and that would be used more widely? And do you know what that shape might be?
Yeah, no, it's a good question, and it's an interesting thought experiment, because generally what we see is that generally as you go up in the complexity of the shape, and so when we go from tetrahedron to a hexahedron, generally that has better properties, right? And so we saw that on Monday when we saw that the quadrilateral or the rectangle has better properties than the triangle, at least in terms of determining solutions. And so that's certainly true, and there's no reason not to believe that if we go up to like a five-sided shape, then that's going to be even better. And so the limitation there is not really in terms of the mathematics, it's actually in terms of the geometry, right? And so a lot of people have already kind of experienced that even when you make the transition from like a triangular shape and you go from a tetrahedron to a hexahedron, it already becomes a lot more difficult to mesh, right? You either get an error from ANSYS, or you get that warning message where only a certain percentage of the mesh is hexahedrons. And so that issue compounds. It becomes exponentially even more difficult as you make the shapes kind of more complex as well. And so right now, there isn't an algorithm out there that can mesh any geometry with an arbitrary shape. And so it's one of those questions where, like, if you are able to determine that kind of algorithm, you would stand to make a lot of money, because then you could sell it to ANSYS and all the finite element companies, and you would improve the algorithms quite a bit. So honestly, that's kind of the extent of my own knowledge about it. I don't know too much about meshing algorithms. I have a basic understanding of how they work, but it is something that's basically the bottleneck right now. And I don't think, just based on my knowledge of the field, I don't think there is a lot of interest right now in terms of making that measure. It's more of an academic question right now, more than a practical one. Yeah.
Thank you, sir.
Yeah. Okay, so why is it that we have this relationship where we have one term in our shape function per node? It has to do with the fact that when you make a finite element mesh, the mesh is comprised of a tons of these elements, and they all have to sit next to each other. Okay. And when you have elements that sit next to each other, you want to make sure that your solution is consistent when you move from one element to the next. Okay. And so, FEA really wouldn't be that useful if you compute the solution to be equal to something in one element, and then, in the neighboring element, at least on the parts where they're touching, where they're matching, you get something completely different, right? And so that's what's called an inconsistent solution. And so that means, actually, let me draw it with triangles. Triangles is even easier to draw. And so let's say that we have two triangular elements next to each other. Okay. And so you can see these two triangular elements are, touching at these nodes, right? And so what that means that those nodes are kind of the points of connection in between those elements, right? And so to make sure that, the solution is consistent when you go from one element to the next, those nodal solutions should be the same everywhere, okay? All right, so what that means, go ahead and draw this this two element system again. So what that means that, if we label these nodes, and so we say this is node 1, 2, 3, 4, okay? And so anytime you have a mesh, each node in the mesh is given a unique ID number, okay? Just so that we can refer to them later, right? That means that the solution values, and so we'll call it T1, T2, T3, T4, okay? The solution values at the nodes should be consistent everywhere. Okay. All right, so how does this factor into the shape functions? Okay. And so we can use the fact that we require these nodal solutions to be consistent to solve for the unknown coefficients in our shape function. All right, so what does this look like? And so let me just kind of remind you, because I switched back to triangles here. And so for a linear triangle, okay, so for a linear triangle, our shape function, which is t of xy, is equal to c0 plus c1x plus c2y, right? We had three terms in our shape function because we had three nodes on the linear triangle, okay? And so ideally, we would like to solve for the values of each of these coefficients, right? So C1, C0, C1, and C2. Okay. And so if we wanted to solve for the values of these coefficients, that means we need at least three algebraic equations. Okay. Those three algebraic equations are basically, we obtain those by forcing our solution to be consistent at the nodes, okay? And so for instance, if I were to look at this element right here, okay? Basically our three equations would look like this. And so we say T1 okay, which is the solution at node 1. It's going to be equal to C0 plus C1 x1 plus C2 y1, okay, where x1, y1, x1 and y1 are the coordinates of node 1. Similarly, we can write another equation for node 2. Okay, so T2 is equal to C0 plus C1 x2 plus C2 y2. T3 is equal to C0 plus C1 x3 plus C2 y3. Okay. So let me just complete this. So x2, y2 are coordinates. Two, x3, y3 are coordinates. So that's basically the reason why we have this. And so, you know, because we need the solutions at the nodes to be consistent, just to have a consistent solution throughout, we can use that fact to solve for the unknown coefficients in the shape function. Okay. Of course, you know, I'm not going to actually solve this system because it's all in symbols, and it'll probably take me, you know, at least 45 minutes to do that. But you know, you can see that it is possible to solve C0, C1, and C2 with these equations. Okay. All right. Any questions on this? Okay. All right. And so of course, you know, the more nodes that you have, you know, the more equations that you're going to have. And so that makes the cost, you know, even more difficult. Okay, so that's the linear tetrahedron. Okay, so a linear tetrahedron is kind of the simplest element that you can have in 3D. Let's go ahead and move up in complexity. So let's cover the quadratic tetrahedron. Okay. All right. So let me go ahead and draw our usual tetrahedron here. Okay. So just like before, we're going to draw nodes at each of the corners. So we have 1, 2, 3, 4. Okay. And then just like we did in 2D, in order to add more nodes to the system, we're going to add mid nodes, right? So in the middle of each of the edges, we're going to add more nodes. Okay, so we're going to node here, 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 and here. Okay. And so if we continue with the numbering, we have 5, 6, 7, 8, 9, and 10. Okay. All right, and so of course, you know, we have 10 nodes, and so that means we have 10 terms in our shape function. Okay, so let's go ahead and write that out. So we have t, x, and y is equal to C0 plus C1x plus C2y plus C3z. Okay, so those are all of the straight up linear terms. Okay. Next, let's write out all the straight up quadratic terms. So we have C4 x squared plus C5 y squared C6 z squared. Okay. All right, so that's 7 terms. We need 3 more. And so for the last 3 terms, we're going to include all the cross terms, right? So we have C7 xy plus C8 xz plus C9 yz. So you can see, quite a significant increase in cost, right? And so if you compare the number of nodes in the quadratic tetrahedron, it's 2.5 times more than the linear one. Okay. And so generally, this is kind of true. So as you go up in dimension, right? So you go from 1D to 2D to 3D, making these decisions of whether you use a a triangle versus a triangular element versus a rectangular element, just the increase in cost is going to be greater. Okay. And so you can see here the decision to go from linear to quadratic in 3D is basically a 2.5 times increase in the cost. Okay. But you get a lot out of it, right? And so what you get out of it is a much more robust, a much more complex shape function equation. Okay. And this leads to much better solution behavior. All right, any questions on this? All right, so before we move on to the hexahedrons, let me just remind you of some of the useful properties for tetrahedrons. Okay. So this applies to both linear and quadratic. And so remember, tetrahedrons have what's called the simplex property. What the simplex property basically states is that they're able to fill any three-dimensional space pretty much exactly. And of course, this is really useful if you, if you have a complex geometry and you want to make sure that it's going to mesh. And so, using tetrahedrons for that, as at least for a first step, is really useful. Okay. That's the quadratic tetrahedron. Okay. Now let's move on to the rectangular elements. So let's start with the linear hexahedron. Okay. And so the linear hexahedron looks like this. And so it looks like just like a box, literally. Let's go ahead and label the nodes, 1, 2, 3, 4. I'm kind of labeling them at random, and so you don't have to have the same labeling convention as me. As long as you get to the same number of nodes as I do, that's what's most important. So if you count the nodes on a linear hexahedrons, you can see we have 8 nodes. And so what that means is that our shape function is going to have 8 terms to it. So let's go ahead and write that down. So our shape function, t of x, y, z, is equal to, same thing. So we're going to start with our constant term, then our purely linear terms. So you have C1x plus C2y plus C3z, okay? If you notice, that's where we stopped for the linear tetrahedron. And so for the linear hexahedron, we actually have 4 more terms that we can play with, okay? But remember, this is a linear hexahedron. So technically we shouldn't go into any explicitly quadratic terms, okay? But we can do all the cross terms, right? So if we do C4 xy plus C5 xz plus C6 yz, okay? So I know technically those aren't strictly linear terms because you have 2 variables multiplied by each other. But again, they're what we call pseudo-linear because in each individual component or each individual dimension, it is linear, okay? And then finally, we need 1 more actually. So even with the cross terms, we're not at the 8 that we need. And so we need to add 1 more. And it's going to be the triple term xyz. So that is our shape function for the linear hexahedron. Okay? You can see a lot more complex than our linear tetrahedron. Right. So this is really interesting. And so this is where kind of the differences in elements actually start to become interesting. If we look at our last term here, right? This is our triple term, XYZ. Okay? Let's look back at our quadratic tetrahedron. Okay? So if we come back up here, and if we look at each term in this expression, and so while it's true that we do have quadratic terms here, we have x squared, y squared, and z squared, there's no xyz term. Okay? And so in 3D, we actually get this very interesting case where like the linear hexahedron is actually able to capture some solution behavior, some solution patterns that even the quadratic tetrahedron cannot handle. Okay? And so this kind of gives more evidence to the fact that, if you are able to get a hex mesh, you can see that even in the linear case, there might be some situations where you get better solution behavior with a linear hexahedron versus a quadratic text, okay? That's if your solution depends on X, Y, Z. Okay. Any questions on this? All right, and so when I say that, you can get better behavior, what I mean by that is that if your solution or if the underlying true solution has strong dependence on XYZ, then you're going to get better results with a linear hex versus a quadratic text. Okay. Because remember how FEA works. And so remember, FEA works by first assuming a form for the solution. Okay. This shape function is our assumed form, right? And then from the assumed form, we basically find the values of the coefficients so that they match the true solution as best as it can. Okay. So if you have kind of strong dependence on certain terms, then it helps to have those terms in the shape function. Okay. So that's why, when I say more terms is better, more terms means that we have more opportunities to match different kinds of solution patterns. Okay. Okay. But of course, this comes at a cost. The cost being that it's much more difficult to produce a hex mesh than a tet mesh, especially for more complicated geometries. Okay. All right. So I've been stalling long enough. So let's go ahead and get done with it. So let's do the quadratic hexahedral. So this is going to be the quadratic version of what we just drew. Make sure I give myself sufficient space here. Okay, so there is our box, our hexahedron. Okay, so let me start out with all the corner nodes. One, two, three, 4, 5, 6, 7, 8. Okay. And so now we're going to add all the mid nodes. And so, if you're familiar with the box, you know that there's 12 edges to the box. And so we're going to add 12 more nodes to this guy. Okay. 1, 2, 3, 5, 6, 7, 8, 9, 10. Good. Okay, so let's continue with the numbering. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I always forget the one in front. All right. And so we have 20 nodes in our element. So that means we have 20 terms in our shape function, right? And so, it's going to be long, right? But 20 terms also means that our solution is going to be whatever solution that you obtain from a quadratic hexahedron. It's going to be good because you're able to capture, basically 20 dimensions, or no, that's a bad term. So 20 different ways that the solution can vary. Okay. And so, if you're able to get a quadratic hex on your mesh, a lot of times the cost is worth it, because a lot of times, people call this, like the Rolls Royce or the filet mignon or the Whole Foods of finite elements, right? So this is kind of as good as it gets, right? At least in terms of the limitations of what we can actually reasonably mesh. Okay, so let's go ahead and start. All right, so our shape function T of X, Y, Z. Okay, so we're gonna have 20 terms here. So we start with our constant term C0. Then we have all our linear terms, so C1x, C2y, C3z. Okay. I'm going to skip right ahead to the quadratic terms. And so we have C4x squared plus C5 y squared plus C6 z squared. Okay. We have all the cross terms, and so we have C7 xy plus C8 xz plus C9 YZ. Okay. Then we start to have the cross quadratic terms. So this is where most of the new terms come from. Okay, so C10 x squared y plus C11 x squared z plus C12 y squared x plus C13 y squared z plus C14 z squared x plus C15 z squared y. Okay. All right, then we have all the triple terms. And so we have plus C16 xyz plus C17 x squared yz plus C18 xy squared z, and finally C19 xyz squared. A lot of terms, and so definitely not something you want to definitely not something you want to solve by hand. So this is definitely something we'll leave it up to the computer, because the computer is much better at solving these things. Okay. Any questions on the quadratic hexahedron?
I have a question, sir.
Sure.
That equation that's boxed, you could also write that in a matrix form, right?
Yep, sure. Yeah, you can definitely do that.
Sounds good.
Yeah, I mean, normally this is not something that you would solve by hand. I'm showing it here just for, just to kind of demonstration purposes. But yeah, so if you did want to solve one of these by hand, you'd probably use a more convenient form like a matrix. Yeah. Okay. All right, and so that's that's all of our element types, right? And so we've gone over the 2D elements. So we went over the triangle and the rectangle, as well as the 3D elements, the tetrahedron and the hexahedrons. We've looked at their linear and quadratic forms. Okay. So now, hopefully you have a better kind of understanding of kind of what you're kind of choosing when you make those decisions. Okay. So there's kind of a lot that goes under the hood. And so next thing I want to do is to kind of, just kind of condense everything that we've learned kind of in the last 2 lectures into kind of a simple, kind of easy to read kind of format. Okay. Because, I know, probably what everyone's thinking of right now is the projects, right? And so a big part of the project is to, when you make a decision in terms of, what type of element that you're going to use for your mesh, right? Whether the, talking about the shape as well as the order, okay? You have to be able to justify it, right? And so let's kind of make a comparison table about all the different element types so you can see what are the pros and cons of each. So I know we kind of talked about this a little bit. So when we went over meshing basics, much earlier in the semester, we talked about this a bit. But I think now that we have kind of this knowledge of the, what all the elements, at least what their shape functions look like, you have kind of a better understanding of, how much more expensive a quadratic hex is compared to a linear 10. Okay. So the tables are going to look like this. So, on the one hand, I'm going to group together the triangles and the tetrahedrons because they're basically, cousins of each other. Together the quadrilateral and the hexahedrons because again, those are basically the same as well. Okay. One is just in 2D and the other is in 3D. And then I'll make columns for the linear versions of these elements and the quadratic ones. Okay. The way I'm going to do this is I'm going to list kind of pros and cons of each one, and then we'll talk about, and I'll kind of mark them. Okay. All right. So the first pro that we're going to do. Okay. So this applies to both the linear and quadratic versions of the triangle of the tetrahedron. Is of course going to be the simplex property. Okay. And so the simplex property is actually really nice. So this is probably the best, without regards to the shape function, this is probably the best property that you can have in an element. Okay. Because what you'll see is that, as your geometry is getting more and more complex, it gets a lot more difficult to actually mesh them. So to have an element shape that you can fall back on and you can always count on it to give you a good mesh, that is huge. Okay. And I'll say this too, that, we're talking about the quadrilaterals and the hexahedrons, and we talk about their superior solution properties, which is all true. Okay. But with that said, there's nothing wrong with using tetrahedrons as well. Okay. So I will say, I think I mentioned this before too, that I did my entire, dissertation using tetrahedrons. Okay. And so, because remember, one thing that we haven't really talked about, this week is the fact that you can also control how big the elements are as well. Okay, so you can control the element size. And so even though your solution, your shape function may not have, as many terms with the tetrahedron, you can still control for the size of the elements to make sure that you still get a good high quality solution. Okay? It may not be the most efficient thing, but you are still able to get good accuracy with TETs. Okay, so there's nothing wrong with TETs. Okay, and so if you're using them, don't feel like it's a loss or don't feel like it's a bad thing. It's fine. You just have to maybe use a smaller element size than you would have if you could use hexes. Okay, and that's totally fine. Okay, so that's the first kind of nice property for tetrahedrons. Okay. But the downside to this, okay, and this kind of goes hand in hand with the simplex property, is that the thing with tetrahedrons is that they get distorted very easily. Okay. And so this kind of has to do with the fact that a tetrahedron is not kind of a nice symmetrical shape. And so it's kind of a weird, kind of awkward shape, right? And so if you remember when we talked about meshing basics, a few weeks ago, we talked about this idea of mesh quality, right? And so mesh quality has to do with, measuring how distorted your elements are, okay? And so when you use tetrahedrons, even though it can mesh any geometry, that comes with the drawback where if there are kind of like weird curves or weird sections of the geometry, then the tetrahedron is going to distort itself to get into that position. Okay? And you may see that as something that's unavoidable, but that's something that sometimes you actually want it to fail. Okay, because one thing that we'll start to talk about in the coming weeks is that sometimes it's better to work with a kind of a prepared version of your geometry. Okay, because the direct CAD model that you may produce in SolidWorks may not be the most appropriate to use for FEA. Okay. And so what I mean by that is that there are a lot of, I would say, geometrical details that you would include normally in a CAD file that you would not need to include in an FEA model. Okay. okay? So case in point, if you remember on Monday, when we were talking about the project, one thing I mentioned is that in the CAD files that I'm giving you, there are a lot of kind of superfluous or kind of extra details in the geometry that you'd actually don't need for the FEA. So a lot of the nuts and bolts that are in the geometry, okay? And so those ones you are going to want to suppress because it's going to make it more difficult to mesh, okay? And so sometimes sometimes what can happen is that if you use a tetrahedron, which is always going to give you a mesh no matter what, right? It's not going to let you know that there are some of these geometrical features that you may want to smooth over, okay? Some other examples of this would be kind of some sharp corners in your geometry, okay? So if you have some kind of sharp edges or sharp corners, usually for an FEA, what you want to do is you want to fillet those out or kind of round them out to make it a little bit easier to mesh. You get a higher quality solution out of that as well, okay? And so if you go with a tetrahedron mesh right away, it can kind of mask some of these issues where it's a little bit harder to kind of debug them because the mesh just produces automatically, okay? And so sometimes you want to run into errors, but sometimes you want the computer to tell you kind of what are some areas of your geometry that may not be good, okay? And so that's something that can be sometimes hard to determine if you're using tetrahedron elements. Okay. And so let me leave a little bit of room here. One more minus that I wanted to do. Okay, so another minus, and this is shared between both linear and quadratic versions of the tetrahedron. Okay, so it's kind of looking like I'm doing the same thing with both. Okay, so we kind of talked about this already. It's the fact that sometimes you need to decrease the element size even more drastically in order to get an accurate solution. Okay, so it needs smaller elements. Solution, or I should say for good solution. That's certainly true for the linear tet. I would say it's less extreme for the quadratic because for the quadratic you are getting a much higher quality shape function there. Okay, so maybe I'll make that in orange, and so it's not as bad as red. Okay. So it's not as extreme. And so if you're using linear tets, sometimes you have to really kind of kill it with elements in order to get a good solution. You don't need to go that far for quadratic tets. But it's certainly true when you're comparing tets versus hexes. Okay. And so the last minus that I will mention for the linear tet is shear locking. And so when you use a linear tetrahedron with such a simple shape function, you kind of run the risk of running into issues like shear locking, which can kind of really drastically affect your solution. Okay, that's not really an issue for the quadratic one, so I'll leave it off for that. Okay. All right, any questions on this?
I should wait till the other tables are filled, but in general, with the trade-off resolution versus the shape choices, preferences or what from your experience, like which ones do you go?
Yeah, no, it's a good question, and it's definitely an open question that that different people kind of prefer different things. I would say kind of the thing that kind of breaks the tie between the two, because you could argue that for the tetrahedrons, right, you have to include more elements in order to get a more accurate solution. But even though you may use a hexahedron and you use less elements, but each element itself is going to be more expensive, and so you might say the cost might be about the same. And so kind of the thing that kind of tips the scale is a lot of time is mesh quality. And so you look at the mesh and you see how distorted are your elements going to be. And so that's kind of the tipping point. And so you kind of visually look at the mesh and see that if all the elements kind of look neat and kind of neatly organized and arranged, then you can kind of already see that this is good quality. Versus if you use like a tetrahedral mesh, then you look at the same geometry and the elements are kind of distorting themselves in kind of crazy ways. That's kind of the tipping point between the two. But with that said, there's some people that won't even touch hexahedrons, and so they'll just say, I'm just going to do everything in TETs anyway, and I'll make it work. And that's certainly true. Okay. ANSYS actually kind of creates a nice dilemma. It's a nice dilemma to have because the hexahedral measure in ANSYS is actually really nice, and that's definitely not true for most softwares. And so, in reality, even producing just a basic hex mesh is actually really difficult. So the main reason I did everything in TETs for my own research was the fact that I didn't have access to a hex mesher. And so an arbitrary hex mesher is it might be actually a copyright that ANSYS owns that other people can't use. Yeah. Okay. All right. So let's talk about the hexahedrons. Okay. So the main downside that you'll get with hexahedrons is that it can be difficult to mesh. Okay. So it's kind of the opposite of the simplex property. Sometimes you'll run into geometries where it just seems impossible to mesh with the hex, and maybe it is. And so despite how good the hex mesher is in ANSYS, even that has its own limitations. Okay, and I guess I can add to that too is that if you're going to be using softwares outside of ANSYS, sometimes a hex mesh just is not even available. But the good news is that when it does work, it typically works very well. And so the elements that come out from a hex mesh tend to be higher quality. And this higher quality comes in kind of two dimensions. And so on the one hand, the elements don't really get distorted as easily. Okay. But it also comes in the fact that the shape function itself is also much higher quality as well. All right, so one good thing, and I guess this is true for quadratic TETs as well. Okay. Right, so this is kind of something that's unique to just quadratics, kind of in both dimensions. Okay. The fact that you have quadratic terms in your shape functions means that you can capture sharp gradients a lot better. Okay. Okay. And that's actually pretty important too, because a lot of times when you're running FEA simulations, you're going to have situations where your solution is going to change very rapidly over a short period over a short amount of space. Okay? And so this happens a lot in stress analysis. And so a lot of times, especially if you have sharp corners in your model, you're going to have a very high stress concentration in one area, and then it's going to drop down very rapidly from there. Okay. And so you want to make sure that your elements kind of have the tools available to capture that gradient very accurately. Okay. Because a lot of times capturing that gradient well, that's pretty much the rate determining step in terms of how good your solution is going to be. Okay, and of course the one minus sign here that we mentioned before is that even though the shape function is generally higher quality, the additional number of terms and the additional nodes, that comes at additional cost too. Okay, so higher cost per. Okay. All right, so that's kind of the table. So it's Christmas colored. I hope nobody in the class is red, green colorblind. I always forget that, but I can't use red and green together because some people can't read this. For some people, this is all just one color. But, hopefully the colors are helpful for most people. Okay. Any questions on anything here? All right, and so the last note that I'll make, before we talk about shell and beam elements, is to remember that, very much in the spirit of activity 3, you can apply different mesh settings to different parts of your geometry to kind of make your meshing more efficient. Okay. And it goes even further beyond that too, because you can add local refinement. You can add, a boundary layer mesh too. And so there's a lot of things that you can do with the mesh. And so probably not next week, because next week we have an activity. But the week after that, we're going to talk more about what are some of those more advanced settings. What are some of those more advanced features you can use in ANSYS to really modify your mesh, just so that you have all kinds of options available to you. Okay. All right, and so that's all that I have to say about these are kind of what I consider to be the solid elements. Okay, so tetrahedrons, hexahedrons, a lot of times we call these solid elements because they're solid 3-dimensional elements. Okay, there are actually more elements that are available to you, to fit kind of more niche or more kind of interesting situations. Okay, and so we're going to go over 2, I would say, kind of the more common elements that you can use, which are called shell and beam elements. Okay. And so I'll introduce the concept of shell and beam elements just because we don't have that much time left today. We'll expand on it a lot more next Monday. And then Wednesday, we'll do an activity regarding shell and beam elements. Okay. Okay. And so far, we have covered basic solid elements. And so from here on out, I'm going to assume that we're in 3D. Okay. I think all the rest of our activities are 3D as well. Okay. So by solid elements, I mean tetrahedrons and hexahedrons. Okay. So, I didn't really mention this yet, but, the solid elements, even though they're kind of your first option, they're kind of the default option in ANSYS, there are certain situations where they work the best. Okay. And so that usually are cases when your object is relatively well filled out in all three dimensions. Okay? And so what do I mean by that? So filled out, that's kind of a weird kind of way to put it. Okay. Basically, what I mean by that is that if you look at a characteristic length of your geometry in all three directions, those characteristic lengths are all kind of approximately the same. Okay. So let me kind of give you some visual examples. Okay. And so the most basic visual example that you can give is just a cube. Okay. This is literally the perfect example for having filled out in every dimension. Okay. So if you look at a cube, and you look at the lengths of the cube in each direction, by definition of a cube, L1, L2, L3 are all exactly the same. Okay? L1, L2, L3. So this works pretty well because, remember what we talked about in mesh quality, the best elements that are out there are the ones which kind of have this same kind of shape, which is not that distorted, is not that smushed up, is kind of looks basically like this, right? So this is a cube, but this is also kind of the perfect hexagon, okay? So the nice thing about this is that elements, when you go to mesh it, the elements will fill out each of the directions in roughly the same amount of density. Okay. So what's an example of a geometry that's not filled out, right? So, these types of geometries, I like to kind of characterize them as either thin or slender geometries. Okay? So, let's do a very simple example again. And so instead of a cube, let's do a very thin, flat plate. Right, so let's measure the characteristic lengths. Okay, so we'll call this L1, we'll call this one L2, and then going into the page, we'll call this L3. Okay. And so in this case, even though they're not all exactly the same, we can see that L1 and L3 are at least similar. So those are at least approximately the same, right? They may not be exactly the same, but they're at least on the same order of magnitude. But these are much bigger than the last dimension, which is L2. Okay. So this is going to present some difficulties in meshing, okay? Because what's going to happen is that when you mesh this, you're going to choose when you mesh this and you choose a size, you're going to have much greater mesh density in one or two of the directions versus the other. Okay. Okay. So, let me put a mesh on this just so that you can see. Okay. Just so you can kind of see the difference. Let me mesh it in a different color. It started as horizontal lines. I have no idea how they got slanted like that. Let's pretend that that's a good kind of mesh. Okay, it wasn't subjected to my poor drawing skills. Okay, and so you may look at this mesh and you may think that this looks fine, right? So I don't see an issue with this kind of mesh. Okay, but if you count the number of elements, let's say in the L1 direction versus the L3 direction, those are roughly the same. Okay, but what kind of stands out to me in this mesh is that in the L2 direction, we only have one element going through that direction. Another way that we can say this, and kind of the more common term for this, is that we only have one element through the thickness of this geometry. So this is a situation that you want to avoid, okay? Because when you only have one element through the thickness, okay, that means that you have no nodes on the interior, okay? So, assuming that you have all linear elements, okay? And that could be bad because, if you're computing any kinds of variation, if you want to compute the variation of stress or the variation of deformation through the thickness, you're not really going to get any accurate numbers, okay?
Dr. Chan,
Yes.
would this case be okay for a two-dimensional simulation?
We'll get to that in a second. That's kind of exactly where we're moving to. Yeah.
Sounds good.
So even with the quadratic mesh, it would be very difficult to capture variations in that direction. And so, you may look at the situation and, just like Ivan said, maybe this is something that you want to capture or you want to simulate with just 2D elements. Okay. So yeah, I mean, that's fine. And so if this is a plate that's by itself, okay. But what if this plate is part of a three-dimensional geometry, right? So what if this plate is part of, another part of the geometry that kind of curves up like this, okay? And so overall, the entire geometry may be 3 dimensions, but just one part of the geometry is very, very thin, okay? And so, you can't really treat this as just a purely 2-dimensional simulation in that case, because there are 3-dimensional effects, but you still want to, get a good quality solution, okay? The other thing you may say is, like you might say that, we have only one element through the thickness, and so why don't we just make the element smaller, right? And so why don't we just make the element smaller such that, we get an extra element in here, okay? If you're running with some very advanced mesh features, you can do that, and so you can kind of selectively refine in one direction while leaving the other two the same. Okay, but the problem that you'll find is that if you try to make the elements much smaller just to fit within that thin slice, it's going to come at a massive cost, because then it's going to refine in all the other directions as well, and so your mesh is going to look like this. Okay. And so you kind of get the idea, right? And so you end up basically massively increasing the cost, for not really that much benefit. Okay, so that's not really a feasible option as well. Right? So the question is, what do you do in these kind of situations where you have kind of a tricky part of your geometry, where you want to get good accuracy, but you don't want to increase the cost by a lot. Okay, so actually the solution is actually much closer to kind of what Ivan was saying. Was that, why don't we kind of treat this as kind of a pseudo 2D situation, even though our overall geometry might be 3D, okay? So what if we mesh this part with 2D elements, but we use kind of specialized 2D elements or special 2D elements, which kind of maintains the fact that it can still deform and still have dimension in 3 dimensions. Okay. So the good thing is that, of course, this is definitely possible. Otherwise, I would not bring it up. Okay. And so for these ones, we use specialized elements. And so these are called shell. For 2D elements, they're called shell elements. And we'll see that there's also an analog for 1D elements, which are called beam elements. Okay. And so we'll dive a lot more deeper into this on Monday. So we'll talk about, what exact properties do shell and beam elements have? Why can they actually work in 3 dimensions, and how much cost they actually save in practice. Okay? And we'll talk a little bit about how do you actually make these enhances. Okay. All right, any final questions on this before we wrap it up for the week?
So for
That one is a little bit special. So technically that one is, it is a shell. It's technically a shell element because it is kind of a 2D strip, but it was created in kind of a slightly different way. So I guess to answer your question, yes, it is a shell. But the way they created that is different than what we're going to do on next Wednesday. Okay, all right. So that's all I got for today. And so thank you guys for coming out. It's still going to be rainy and cold outside, so please, stay warm, stay safe. Okay. So hope you guys have a good weekend. If you have any questions on the project or anything, please let me know. But if not, I will see you guys on Monday.
Thank you, Dr. Tron.
Thanks, Ivan.
Professor,
Yes.
I have one question. Sorry about that.
Yep.
Question number 8. I'm getting negative 18 in the pounds LBS. I'm getting negative 18 in the negative Y direction.
Okay.
I don't know if it's right. Is that too small? I feel like a cat could break that chair or something.
No, actually that is right. Yeah. So it's
Really?
been a while. It's been a while since I've done this activity. but basically that chair is very poorly designed.
Okay.
That's kind of the conclusion of that one. But yeah, that's I don't remember exactly what I got, but it was a very shockingly low number 2.
Okay, thank you, Professor. Yeah, I was like, dang, like a little chunky cat might have broken the chair or something type of stuff.
Yeah, it's I think I got that CAD file from it was like some design students CAD file. So I feel bad for kind of dunking on some students' work, but you should learn how to design better chairs.
Thank you, Professor.
Yeah. Yes.
When I was doing the third activity,
Yes.
I found many errors. You know what?
So this usually happens it happens for 2 reasons. So one reason it could be that your geometry is under constraint. And so did you add the fixed support on one? Okay. So the other reason this could happen is that the deformations might be a little bit too large. So you can try taking the loads and just reduce them pretty significantly. So I would reduce them by a factor of 10, just for testing. And if you're still getting those errors, just let me know, and then I think I might have to take a look at it. But that's usually the 2.
I mean, I did it and then I redid it.
Yeah.
And then I redid it again.
Yeah.
Then it worked.
Oh, okay.
Like I didn't make any changes.
Oh.
I don't know why that's happened.
There are some situations like that because the solver it depends on kind of how the memory in your computer is arranged. And so it could have been that it was just a really bad, just random assortment of memory, which is very weird. It's rare, but it can happen sometimes. But if it's happening with kind of regularity, just let me know. I can probably take a look. So this is something. Was this kind of another random error that occurred after, or was this something that's happening consistently?
Consistently.
Okay.
Yeah.
All
these errors are happening consistently.
I see. Yeah. So for that one, that's an issue with the meshing. So
First I used multi-zone.
yeah.
Then when I used hex dominant, I think it was good.
Okay. Yeah. So so sometimes
when I used tetrahedral also this happened. The same thing happened.
Oh, that's weird. Yeah, usually the tetrahedron mesh should work a lot more consistently than the hex.
But hexahedral worked.
Yeah. Oh, that's weird. Usually when I get those errors, it's usually some kind of meshing setting that was kind of rogue. And so what I usually like to do then is I take all the meshing settings that I applied and I suppress them. You don't have to delete them, just because if you delete them then you lose them. But you can suppress them, and then so that it'll try to mesh without those settings. And so usually if you go back to kind of
which settings?
like the sizing and the method stuff.
Okay.
And so if you right click on those, you can suppress, and then you can try to remesh after that, and you can see. So a lot of times it's one of those settings that's causing that issue, and then from there you can kind of see.
And then we can find out which setting is causing that issue.
Exactly. Yeah. So usually it's one of those, because usually if you mesh by itself, especially for kind of a relatively simple geometry like this, it should mesh without any issues. And so sometimes if you have a combination of like a certain method like multi-zone or something like that, and the sizing,
I mean,
it can cause issues like that.
multi-zone should be better, right? Better than hex dominant.
In theory,
Because-
yes, but sometimes it can cause some issues like that too. Yeah.
Why got so many? There's a contact sheet.
Oh, okay. So this has to do because for the assembly that we're doing, we have the different parts.
Yeah.
Everything for those is considered bonded, right?
Yeah.
Okay. So sometimes what can happen is that if your deformations are a little bit too large, it can cause those bonded surfaces to separate because the deformations are so large.
Okay, so I should decrease the load again.
Yes. Yeah.
Okay.
Yeah. So that could happen sometimes too. Yeah. How much deformations were you seeing?
I was seeing 9 inches.
Okay, that's not bad at all. It's very strange. If you want to send me your project, I can take.
When I was doing this, I couldn't find the answers. Like the solution was not being.
Oh, it didn't even solve.
No, it didn't even solve.
Oh, it didn't even solve.
Yeah, I just solved it recently.
Okay.
So now it's working.
Okay.
Yeah.
But sometimes
Yeah,
it's,
I was doing this like all
all 2 weeks. I was like doing it
Uh-huh.
and then one more. And load transfer error has happened.
This is the first time I've seen this error, but just based on the text of the
This was the
error-
most consistent error.
Oh, this one's the most.
Yes,
consistent. Okay.
most was like showing every time.
This might be occurring because remember, part of the activity, we have that load that's being applied on a point.
Yeah.
So normally that's bad practice. So normally you don't want to do that. And so what I
You
think,
should be applying it to the entire space.
exactly, yeah. So the wider surface that you can apply a load on, the better. And so if you apply on a point, it can cause some issues. I don't know if this error is directly related to that, but that's kind of what it sounds like to me. Yeah, because it's basically trying to apply a load to a small point.
Small.
And so I think probably what happened was that when the other loads were being applied to it, it caused that point to be kind of distorted, and it had a lot more difficulty applying that. And yeah, so if you're having that issue, so for this activity, I just wanted to show you that you can apply a load at a point, but in 99% of cases, you don't want to do that. And so if you're getting that error, I would try to change that load from that point to across the whole surface. Okay, cool. Yeah, if you're running into issues, you can always email me. So you just email me the issue and then we can chat on it. So you don't have to wait till class.
I mean, I was like, I couldn't do it on my laptop.
Uh-huh.
I don't know, and I did it on the system. So I
Yeah.
was waiting for class to do it on the
Oh, okay. I see.
because it's always closed, right?
Yeah.
So I did it and it worked.
Okay.
And I was like, and then I tried it on my laptop.
Uh-huh.
It worked. I don't know what's happening.
Sometimes it's like that. When you work with computer stuff, it's like sometimes you just can't predict what the computer's thinking. It's like that with code too, right? So you run the code and it's like you don't know what's going on, and you go to sleep and you come back the next day and then it works. And it's like what happened? I didn't do anything. The computer was just cranky last day.
You were teaching only static structure, or
We're mostly doing static structure. Yeah, so we're doing a little bit of dynamics. So dynamics will be activity 5. And what I'll cover.
I mean, will you be teaching CFX?
No, I won't. So I will go over fluids a little bit, but we're doing fluent, not CFX.
Fluent.
Yes. Yes, Fluent is the one. Honestly, both ones I'm not that familiar with because I never used it before. I've learned a little bit. of Fluent.
In my bachelor's, I did my project with Fluent,
Okay.
and I studied ANSYS a little bit, like outside of my bachelor's. Then I studied CFX. I was like, okay.
I see.
It's like
Yeah. CFX I've never used before. So Fluent I have a little experience with. So that's why we'll go over it a little bit in the semester. But it's pretty big. So if you've used Fluent before, you probably know it.
Yeah.
So,
My project was analysis of cavities over aerofoils.
okay.
Yeah,
Very cool.
Yeah, so that was.
Oh, cool.
So it's like it's really fun. ANSYS is really fun.
Yeah, it is. Yeah,
it is really
it's a
fun.
great software.
Yeah.
They do a really nice job of like having everything feel like very tactile. Like every step that you do, you can kind of visually see happening. So I think ANSYS does that better than most other softwares. That's what makes it a great educational tool. But I think it's also really good to work with. Yeah.
Hey, Professor.
Oh, hang on, Chris. He has one more question. Yeah.
The midterm project seems so small. The committed homework, it's small, right?
You mean the CAD file?
I mean, no, the entire. This is like 350 pages.
Yeah.
Midterm is so small.
Yeah, because I mean the midterm,
That's it, right? It's just an
it's-
analysis. That's it, right?
it's just an analysis, but then a lot of it's going to be the methodology too. So it's how you justify how you describe it. Yeah, it shouldn't be that long
I was
because it's
like,
a lot less screenshots.
yeah, a lot of less screenshots. Yeah.
All right, hey Chris, what's up?
First, the internet on your end seems to be unstable.
Oh, was the audio cutting in and out throughout the lecture? Too?
It just gave me an alert that says the internet connection is unstable.
Oh shoot. Okay.
Yeah. Second, for the last part of activity 3,
Yes.
for the meshing, do
Huh?
I need to do a method and a sizing for each individual of the 4 parts, or just one for the seat and back and another for the metal curvy part?
Yeah. So that's fine. So the metal curvy parts, they're basically the same thing. And so intuitively you would think that the same sizing and the same method should apply for both.
Okay.
And
So for the
even like,
seat and for the back, just pick one for both of them or
Yeah,
one for
and
each.
I think one for both are the same too, because usually the meshing that you choose, a part of it is based on the solution, but a lot of it is based on how similar the geometries look. So the seat and the back look very similar to each other. They're basically both rectangles. And so you can apply the same mesh, the same size and the same method for both.
Okay. For activity 3, element size.
Yep.
I cannot remember from 410. What is an appropriate element size? How do we narrow down what is an appropriate element size?
Yeah, no, it's a good question. It's kind of an open question right now because we haven't gone over mesh convergence tests yet. So that
Okay.
mesh convergence test is kind of the main way that you determine how many elements that you need. Because ideally you want to choose a mesh such that if you refine the mesh anymore, your solution is not going to change, right? So you basically eliminate any kind of meshing errors in the solution. For now, I would just choose a mesh such that the number of elements that you get is somewhere close to the numerical limits of the software. So, so if you're using
More the
student,
better.
yeah, like 40, 50,000, 60,000 is if you're in that ballpark, and I can see that the elements are distributed in kind of a way that makes sense. And so you put more elements kind of where the stresses are higher. That's mostly what I'm looking for at this point in the class.
Okay. I've just been going with a number that's near the default for this one.
Okay. Yeah. So
I don't really like I think for activity 2, you told us it's got to be somewhere between a minimum and an average, but I can't figure out how we did that.
Oh, that's for the mesh quality.
Yeah.
Yeah, don't worry about the mesh quality right now. It's going to be really hard to get a good mesh quality unless you really work at the mesh. But that's kind of more time consuming than it's worth.
Okay.
I would just be concerned with just the overall number of elements being in that ballpark of like 30, 40, 50,000. If you're somewhere in there, that's more than sufficient. And then you distribute the elements. You have more elements. If you look at the results, and I see that the stresses are high in a certain region, then there should be more elements in that region because that's where you want the accuracy to be higher.
Okay.
Mhm.
I have a silly question.
Okay.
Are you going to be teaching viscous fluids next year?
I don't know. So I taught it once before. I taught it once in spring 2020. I think
Yeah.
we've offered it once since then, but I was not the instructor for that one. So we have another faculty.
Yeah, Dr. Azazi.
No, actually,
he's the
last time
one.
it was Dr. Myral. So
Oh,
Salvador.
okay.
So he was the teacher for it.
I remember because we spoke to, I think last semester, me and my class, we brought it up with Dr. Azazi about who teaches what. He
Yeah.
teaches the conductive